Hello, pre-calculus students. We will be studying about rational functions. Our objective today is to learn how to graph rational functions with different degree. Our benchmark: use mental mathematics properties and numerical relationships to graph basic types of functions with the aid of tools as computers and calculators. I can apply the knowledge and sense of numbers to solve and represent basic functions of absolute value, square root, linear, quadratic, rational, and step to describe numerical relationships. Vocabulary we'll be using: asymptotes, vertical asymptote, horizontal asymptote, slant asymptote, test values, and degree. What are rational functions? Rational function is any function which can be written as the ratio of two polynomial functions where the polynomial in the denominator is not equal to 0. Here we have our function Rx equals Px over Qx. The domain of the Rx over Qx is the set of all points of x for which the denominator, which is q of x, is not 0. It's represented here in blue. Rx is equal to p of x and qx, or the denominator, may not equal 0. What are the types of rational functions? We have two types: proper and improper rational functions. A rational expression is proper if the degree of the numerator is less than or equal to the degree of the denominator. And improper is otherwise. In other words, the improper will be those that are greater than. Here we have a first example. N less than m. In n less than m, we have x squared plus 2 over x to the third power. If you guys can see here, on the first one, we have x2. So the numerator here, in the numerator, we have the 2. And in the denominator, we have the 3. And we'll always represent the exponent of the numerator. And m will represent the exponent of the denominator. So in this case, it's a proper rational function because n is less than m. Another example of a proper rational function is negative 5x to the fourth power over 3x to the fourth power minus 2. If you guys observe here, our n, or the exponent in the numerator, is 4, and so is the exponent of the denominator, which is equal to 4. Because both exponents have the same degree, then we would say that that is a proper function. Now let's look at the last one. This is an example of an improper fraction: x to the fifth power over 3x squared minus 1. If you guys can see here, in the numerator, we have a degree of 5, which is greater than the degree at the bottom, which is 2. Therefore, this one is called an improper rational function. We are going to do our first example of proper rational functions. We have the first type where n is less than m, or the degree of the numerator is less than the degree of the denominator. And here we can observe the following. If you guys notice, we have the function f of x equals 4x minus 1 over x squared minus 9. If we look at the exponent on the numerator, the exponent of the numerator is 1, and the exponent of the denominator is 2. So it fits the definition. It's a rational, proper function because n is less than m. So our first step here is to find the intercept of x. And where do we look? Always that we want to find the intercept of x, we're going to look at it at the numerator. So we're going to write 4x minus 1 equals 0. So we're going to isolate for x, and this would equal 4x equals to 1 And then x equals 1/4. And we could write it also as a decimal. The 1/4 can be represented as 0.25. So for graphing rational functions, basically, we will have 6 steps. Okay, this is a 0.25 here, or 1/4. And after we find our 0.25, let's erase here a little bit, we will find our vertical asymptote. Step number 2. Find the vertical axis as the denominator. Here we have a difference of square, x squared minus 9. So you guys could figure out this as x plus 3 and x minus 3, or you could simply use your radicals. So x squared minus 9 equals 0, x squared equals 9. Then we can square root both sides. And then we would have x equals 3 and x equals -3. Okay, once we have these two, this is our vertical axis. You could do it that way, or you could also do it as a difference of squares. Remember that x squared minus 9 is represented as x plus 3 and x minus 3 equals to 0. So you have this other option that comes from the factoring techniques that we learned on the last lesson. So we have x equals -3 when we isolate for the first x, and x equals +3 when we isolate for the second x. Okay, so we have our step number 2. Step number 3 is to find the horizontal asymptote. In this case that we have n less than m, our horizontal asymptote will always equal y equals 0. This would be like the rule, right? So here we would have the horizontal asymptote, and it says here, find a possible intercept on it. Okay, so if we want to find an intercept on it, we're going to get the main function, which is 4x minus 1 over x squared minus 9, and we're going to equal it to the value of the horizontal asymptote. In this, we have that the value of the horizontal asymptote is equal to 0. So to get rid of our denominator at the bottom, we will be multiplying x squared minus 9 to both sides. So if you guys see here, in the left side, x squared minus 9 gets canceled, and then we have that 4x minus 1 will equal 0 because that's the product on the right side. All right, so once we have 4x minus 1, we isolate for it, and we actually found out that is the same intercept of x, right? So it says x equals 1/4. Why does this happen? Or 0.25. Basically, when we make our horizontal asymptote, our asymptote will be actually on top of the x-axis, because this is what it says. It says that y is equal to 0. So if we go here and we draw our Cartesian plane here, this is our x, and this is our y, and it's saying that the horizontal asymptote is y equal to 0. So if we would draw that, that would be exactly on top of the x-axis. So because we cannot break down the x-axis, we will just imagine that that is our tiny barrier or wall where our graph will get close to, but if it will be crossed, it will could not be dashed, sorry. So this 0.25 will just be there right here, and because imaginarily it will pass through it, it will be an intercept on the horizontal asymptote, but we will not touch that asymptote. Step 4. Find the y-intercept. When we want to find the y-intercept, what we're going to do is that we're going to evaluate in 0 the function. It gives us positive 1/9, and positive 1/9 is about 0.11. Now that we have the x-intercept, the vertical asymptote, the horizontal asymptote, and the y-intercept, we will graph the following with the information. Going to graph the rational function and 4x minus 1x squared minus 9. So here we have the information. First of all, it says that we have the intersect, sorry, 0.25. Here we go. Then we have the vertical asymptotes, positive 3, always a vertical dash line, and also x equals -3, a dashed line. Then we are going to place here the additional values to complete the graph. Our first additional value here would be -4 and -2.42. So here we're going to put -4 and -2.42. Here we go, our little dot here. Okay, then we have -1 and 0.63. our other dot. Then we have 1 and negative 0.37, really close here. Negative 0.37. So we're going to put here negative 375. Okay, with 1. This is going to be our dot here. And then we have 4 and 2.14. So here we got 4 and 2.14. So here we're going to give here a 1, a 2, and a 2.14. Oh. 4 and 2.14. So once we have completed this, we're going to follow the information that is on the table. It says from negative infinity to negative 3 is under the x-axis. So here we have like a little ear. Then we have from negative 3 to 0.25 at the top. And it says from 0.21 to 3 at the bottom. So we're just going to connect the points that we have here. And we also, just to add here before we forget, we had a y-intercept that was 0.11 just here, which will help connect these points here. So here we go. 0.11 from that y-intercept. Please don't forget it. And here we have the 4 and the 2.14 that says above the x-axis. So this is how our graph would look. We do it with all the points. So this is step by test. You can pause the video and check the information. And here we have a like the polished version of the graph, so you can see it at detail. On part 2 and 3, we will be studying n equals to m or n greater than n. Thanks for watching.